We'll start our lecture by technological foundations of mechanical engineering, and today is theme 4. The name of theme, design of technological operations of mechanical processing. Write down to your notes the theme of our lecture and plan.
Okay, teacher.
4.1, the structure of the construction of processing operations. 4.2, development of technological processes using structural layouts of fixtures. 4.3, selection of equipment and technological equipment. And 4.4, varieties of standardized machine tool fixtures. Purpose of our lecture to learn how to develop technological processes with the use of adapted structural layouts, how to choose equipment and technological equipment and fixtures. And now we start item 4.1, the structure of the construction of processing operations. When designing a technological operation, the following interrelated works are performed. Choose the structure of construction of the machining operation. Clarify the content of technological transition in the operation. Choose the model of the machine. Choose technological equipment. Calculate processing modes. Calculate the time limit. Determine the category of work. Substantiate the effectiveness of the operation. Write down to your notes all these interrelated works. The design of an operation is a multivariate task. Therefore, the assessment of possible options is carried out on the basis of technical and economic calculations. When designing individual operations, they specify the technological road for manufacturing the part and make the necessary adjustment to it. When designing the structure of machining operations, one should strive to achieve a more economical option. An important factor affecting the cost of productions is the productivity of the process, which is estimated by the labor intensity of a unit of production, that is artificial time. As you know, the main components of artificial time are the main and auxiliary time. In this regard, when forming an operation in order to possibly overlap the elements of the main and auxiliary time, different schemes for constructing operations are considered. A, B, and C. A. The number of simultaneously installed blanks over pieces, single and multi-set schemes. Single and multi-set schemes. B. The number of tools involved in processing, single tool and multi-tool processing. The order of using tools, serial, parallel, and parallel serial processing. By different combinations of listed futures, it is possible to construct different processing schemes. We can choose different combinations of the listed futures. Write down to your notes these three different schemes for constructing operations. It's first tool, yes?
Yeah, it's the first one, yeah.
Second
The
tool,
single one.
tool number 2.
Is the first one, I think, teacher.
Tool number 3.
Because of
Number
the rings,
4.
because of the hole in the front.
And you continue. Next tool.
Is changing, teacher.
We use this tool before, so we can not calculate this tool.
Yeah.
This cutter we use in previous operation. Or it's a new tool. Tool for milling.
Yeah.
And now you can see how many tools have this.
Oh, yes, teacher. It's a factory.
No, it's one machine. And this one machine have so many tools.
Okay, yeah.
More than 30 tools this machine have in his magazine. And it's process of changing the tool.
Oh, yeah.
It's tool to make teeth for gear teeth.
The gear now, yeah.
drilling, another tool for milling.
Yes, teacher.
So how many tools we use to machine our workpiece?
It's 4, teacher.
It's so many tools. So
Yeah.
it can be single tool.
Yeah.
Sequential tuning. We use B, sequential processing with several tools. We use several tools and sequential processing. It was B. So in figure 4.2, excuse me, shows examples for multi-place processing. Multi-place processing. A. Single tool sequential processing tuning a set of rings. You can see 1 ring, 2 ring, 3, 4, 5, 6, 7, 8 rings in the set, and 1 tool. Single tool sequential processing tuning a set of rings. B. Multi-tool sequential processing. B. Tool number 1 and tool number 2. And what we have? We have part number 1, number 2, number 3, number 4 in a set. And we use first tool and then second tool. So it's multi-tool sequential processing. Drilling first tool, drilling, and then inking holes in a set of 4 workpieces. C. Multi-tool, tool number 1 and tool number 2. Multi-tool parallel processing, milling grooves simultaneously in 2 parts. Part number 1 and part number 2. So it's multi-tool parallel processing. Multi-tool because we use 2 tools, and parallel processing because we use its parallel in the same time, not one by one, but in the same time. So it's parallel processing, multi-tool. Milling grooves simultaneously in 2 parts. D. Multi-tool parallel sequential processing on a multi-spindle semi-automatic lathe with a round rotary table. It's round rotary table. Rotation of this table, and we have first position, second position, and third position. In first position, loading and shooting of the workpiece. In second position, simultaneous drilling of 4 holes. First, second, third, and fourth holes. So in this position, simultaneous drilling of 4 holes. And in third position, simultaneous countersinking of these holes. And again, we rotate to the first position. So D, it's multi-tool, parallel sequential processing. In the latter case, to perform the transition in the second and third positions, independent power heads with a personal drive are used to ensure tool rotation and feed. When using such a machine, auxiliary time is spent on tuning the table to the next position and on approaching and retracting tool heads. The choice of a specific scheme for constructing an operation largely depends on the production program and the dimensions of the part. In case of single-piece production of parts of any size, single tools, sequential machining will be the most rational. And in serial and mass production of small parts, multi-place, multi-tool, parallel or parallel sequential machining will be the most rational. One of the criteria for the effectiveness of building operations is the evaluation of processes by the coefficient of combination of operational time. Operational time is the sum of the main and auxiliary time. The coefficient k suffix 0 is determined by the formula number 1. So write down to your notes this formula, and in this formula t suffix 0 is the main operation time, t suffix b auxiliary operation time, and n the number of elements of the operation. So write down to your notes the formula to calculate coefficient k0. It's the coefficient of combination of operational time. When required. When designing multi-instrument setups, it should be kept in mind that there is a certain number of tools that is optimal for performing a specific operation. In figure 4.3 shows the dependence of artificial time on the number of tools M used for the operation being performed. Its time and number of tools. As M increases, the main time, T suffix 0, the main time, decreases, but the time auxiliary is increased. So increase for changing time it's for changing and adjusting the tool increases. If we have many tools, the time for changing and adjusting the tool will be increased. If we accept the elements of piece time for setting and removing the workpiece as constant, the total curve of piece time will be obtained by adding the curves t suffix 0, tb, and tp. The optimum value of number of tools, M optimum, occurs at the minimum piece time. In this scheme, you can see the optimum number of tools that we use in one operation. When designing an operation execution scheme, in addition to evaluating options in terms of productivity, one should simultaneously evaluate options and processing costs. And now we start item 4.2 of our lecture. Development of technological processes using structural layouts of fixtures. The choice of an effective variant of the technological process of machining parts is a responsible task for the technologist. The criterion for the effectiveness of the technological process is, first of all, the lowest possible cost of the product while ensuring the required quality. To speed up the choice of an economically preferable option, accelerated approximate methods of calculation are used. Such express calculations should be based on the determination of costs for items that are especially characteristics of each processes. The comparative assessment of which ensures sufficient reliability of the preliminary choice made for further detailed development. Often the required amount of tooling is decisive in choosing the optimal technological process. The cost-effective option is considered to be the one for which the sum of capital investments in devices and the costs associated with their operation is minimal. However, the problem is that the task for designing devices is issued after the development of the technological process for manufacturing the part, and the express calculation is made before its development. That is the cost of adaptation must be calculated even before their design. But without having a specific design of the device and not knowing the type of operation for which it is used, it is impossible to determine the capital investment in it and the costs associated with its operation. Therefore, before processing with the development of the technological process, the composition of operations and accordingly the adaptation for them are determined. Then, with some data on the proposed fixtures, one can calculate the approximate costs of detailed design and manufacture of fixtures, as well as the cost of operating these fixtures. Some data refers to any information that allows you to determine the approximate costs. By comparing different options for operations and devices for them, you can get the optimal combination of capital investments in the device or in the fixtures and the associated costs. The resulting optimal variant of operations and fixtures is taken as the basis for the detailed development of the technological process of machining the part. Thus, the design of the technological process is divided into two stages. At the first stage, operations and devices or fixtures are selected taking into account their economic efficiency. And at the second stage, a detailed development of the technological process is carried out based on the choice made at the first stage. The stage of selection of operations and the synthesis of structural arrangements of fixtures is fundamental for calculating the costs of manufacturing and operating fixtures. The stage of determining the labor intensity of the production of a fixture service as a transition to the calculation of costs. As already noted, at the first stage, any information about the fixture can be used to determine the approximate costs. Ideally, this is the design of the device or fixture. But the detailed design of fixtures in itself is a rather laborious process and therefore is unacceptable at the first stage of the development of the technological processes. We can only talk about preliminary design, during which the so-called constructive layout of the device or of the fixture comes out, meaning a structure consisting of certain elements. The structural layout of the fixture is a model of the fixture that reflects two aspects. On the one hand, it determines the basic design of the fixture, and on the other hand, information that allows you to determine the costs of manufacturing the fixture and the costs associated with its use. For a visual representation of the layout of the fixture, computer-aided design is used. Having special software CAD software. The developer builds a sketch drawing on a computer, which indicates the installation, clamping, guides, and base elements of fixture. The installation elements are arranged in accordance with the typical installation scheme, and the clamping elements are arranged with the typical clamping scheme. Mounting, clamping, and guiding elements must be typical. Their designs can be borrowed from reference literature or create your own library of typical elements. Thus, the developer practically does not deal with the detailed design, but using ready-made templates, which greatly simplifies the synthesis of the structural layout of the device or of the fixture. Simultaneously with the construction of the drawing, information about the elements of the fixture is entered into a special table called the inventory of the fixture, which is used later when calculating the cost of manufacturing the fixture. Information about typical fixture elements includes the element type and its standard size. The body is considered as a set of surfaces, each of which is characterized by design parameters: shape, dimensions, quality, roughness, and type of finish. In addition to the design features of the fixture, the value of the labor intensity of manufacturing and the cost of manufacturing the fixture, indicators of manufacturability, are entered into the inventory. The cost of manufacturing a device can be determined directly in view of the complexity of its manufacture. The costs associated with the use of the device or of the fixture are determined by the complexity of the operation for which the device is intended. The complexity of manufacturing the entire device is calculated as the sum of the labor intensity of manufacturing the elements of the device. Since the mounting, clamping, and guiding elements of the fixture are typical, the complexity of their manufacture is taken from the database of typical elements. The complexity of manufacturing the surfaces of the body can be calculated by the formulas for calculating the complexity using as initial data the design features of the surface, dimensions, quality, roughness, and the type of processing. The structural layout of the fixture allows you to determine the approximate costs of manufacturing the fixture due to the laboriousness of its manufacture and is the basis for the implementation of the method of two-stage design of technological processes for machining parts. And item 4.3, selection of equipment and technological equipment. First stage is its choose of equipment. The choose of equipment basing with an analysis of the formation of technological transitions during the processing of individual surfaces of the part. When developing a technological road for manufacturing a part during the formation of individual operations, they choose the type of equipment, tuning, milling, drilling, etc. Specify the model of equipment, taking into account the requirements that must be met when performing this operation. The technologist must have passports of different models of equipment, which contains their full specifications. And now let's see the video about difference between tuning and milling. Difference between tuning and milling.
Welcome to Academic Game Tutorials. In this video, we will look into the differences between turning and milling processes. Conventional machining is one type of manufacturing process in which excess material is removed from a preformed blank by shearing in the form of chips using a wedge-shaped cutting tool in order to get desired shape, finish, and tolerance. There exist several machining processes to efficiently machine a wide variety of materials in innumerable ways. Turning and milling are just two examples of such machining processes. So, let's look into the basic differences between turning and milling processes in a tabular form. Difference number 1. Turning is performed to generate a cylindrical or conical surface, whereas milling is performed primarily to generate a flat surface. Number 2. Machine tool that is used for turning operation is called lathe, whereas milling is carried out in milling machine. Number 3. Turning process utilizes a single-point cutting tool, called SPTT, which is short form for single-point turning tool, whereas milling process utilizes a multi-point cutting tool, called milling cutter. Number 4. In turning, cutting tool continuously remains in contact with workpiece during the operation, whereas, in milling, tooth continuously engages and disengages during operation, intermittent cutting. Number 5. In turning, the workpiece is rotated at fixed revolutions per minute. This rotation provides necessary cutting velocity, whereas, in milling, the cutter is rotated at fixed revolutions per minute. Rotating cutter provides necessary cutting velocity. Number 6. In turning, feed motion is derived by moving the cutting tool carriage, whereas, in milling, feed motion is derived by moving the workpiece, workable. And difference number 7. Turning can produce fragmented, discontinuous, or continuous chips based on work and tool materials, cutting parameters, etc., whereas milling inherently produces discontinuous chips.
So it was choose of equipment. We can choose equipment for cutting, for tuning, or for milling, or for drilling. When choosing equipment, consider the following factors. Write down all these factors to your notes. A. The dimensions of the working area of the machine, which must correspond to the dimensions of the workpiece or several workpieces. B. The possibility of merit in the processing of the required accuracy and surface roughness. These reasons should be taken into account in particular when finishing and when we have finishing operations. C. Corresponds of the power, rigidity, and kinematic data of the equipment to the most advantageous modes of performing the operation. D. Ensuring the required productivity in accordance with a given program for the production of parts. E. Compliance of the equipment during the performance of this technological process with the requirements of safety and in industrial sanitations. F. Compliance of the equipment with a given program according to the criterion of the cost of manufacturing a part. If for the developed operation it is possible to use machines of two different models that provide the same requirements for the quality of processing, then the device factor or fixture factor in choosing a model will be to ensure the economics of processing. In this case, you should perform feasibility calculations of the cost, which should take into account in particular the costs of operating the equipment, depreciation costs for current repairs and maintenance of equipment. Write down to your notes from A to F factors that consider when choosing equipment, when we choosing equipment. And next stage is the choose of cutting tool. After choosing equipment, we have choose of technological equipment. So, choose of technological equipment. Simultaneously with the choose of equipment, a fixture, cutting and measuring tool are selected. When choosing tooling, one should take into account the type of production, the type of product and its production program, the nature of the intended technology, and the possibility of maximizing the use of existing standard tooling. The choice of fixtures or devices. The choice of fixtures is highly dependent on the parts program. In single and small scale production, fixtures of a universal type are widely used. In serial production, universal reconfigurable devices are devices or fixtures and fixtures for group processing. It's in serial production. In mass production, high performance special fixtures justify themselves economically, which make it possible to drastically reduce the time for installing and fixing the workpiece before processing and removing the workpiece at the end of the operation. If it is possible to use two designs of standard or normalized fixtures that equally meet the requirements for machining accuracy, then the choice is justified by economic calculations. Feasibility studies are required when designing a special fixture design. The choice of cutting tool is made taking into account the processing method, the material of the workpiece, its size and configuration, the required quality of the workpiece surface, and the program for the production of parts. When choosing a cutting tool, they are primarily guided by the use of a standard tool. However, for individual operations, especially in serial and mass production, a special tool is provided. Hard alloys are widely used for the cutting part of the tool, providing high cutting speeds. At present, the use of diamonds, natural and synthetic, is expanding, especially in the processing for non-ferrous metals and alloys, bronze, brass, aluminium, alloys, etc. The costs associated with the use of cutting tools are one of the components in the cost of production. Next stage is the choice of measuring instruments. Is made taking into account the compliance with the accuracy characteristics of the instrument, the accuracy of the size being performed, the type of surface being measured, and the scale of production of parts. In the conditions of single and small scale production, mainly universal tools are used. Calipers, micrometers, inside gauges, universal indicators, devices or fixtures, etc. With an increase in the scale of production of parts, the use of boundary gauges, templates, various control devices, and automatic controls increases. And now we have item 4.4, varieties of standardized machine tool fixtures. To date, a number of technological tooling systems have been developed. The belonging of the design of technological equipment to a certain system is determined by the rules of its design and operation. Systems are formed by complexes of technological equipment designed to perform various types of work. Technological equipment systems include universal non-adjustment fixtures, UNF. These are cam chucks, divided heads, rotary tables, machine vices used in single and small scale production. Next time, Next type, universal prefabricated fixtures, UPF. This is an assembly of prefabricated normalized parts and assembly units of machine tools, assembly and control devices which are disassembled after use. A typical set of UPF parts and assembly units consists of 8 groups. Next type, it's collapsible fixture, CF. The CF system, unlike U and NF, along with typical parts and assembly units, contains special ones, the number of which reaches up to 10 to 15%. Next type, universal adjustment fixtures, UAF. The UAF system is based on the use of a set of debugging variables fixed in the UAF. Specialized debugging fixtures, SDF. The SDF system is intended for a certain group of manufactured restored parts. Such equipment is used in the execution of group technological processes. And the last type, non-separatable special fixtures. Non-separable special fixtures. The NSSF system is designed and manufactured to perform one specific operation. Its use is justified in mass and large-scale production. So, we finished our lecture. Our lesson is finished. Have you a question about our lecture? So, if you haven't the question, our lecture is finished.